Hello, everyone. Good morning and good evening, depending on where you've joined us from. My name is Shantanu. I'm the creator of the Astro Geek Comics, and thank you so much for joining in the first episode of Keeping Up with the Universe. So, before we begin, let me just tell you a little bit about what this series is about. Keeping Up with the Universe is actually a little step that I've taken to bring what's happening on the frontiers of astronomy research, what the scientists are doing, what the professionals are doing closer to the public so that they can better understand what is going up in the night sky. Because I realized that even though if I may try to stay updated about the news every day, a lot of things are happening, and some of these things, the people should be directly talking to the scientists for that. So today's first episode is called Understanding Cosmic Fireworks, right? So there are some wonderful fireworks going up in the sky, right? These fireworks can be actually very dangerous if you're standing very close to them, but from far away, they are going to tell us a lot about the universe. And with me today, I have a very special guest, someone I came across during my this journey of scicomm, a very great science communicator. His name is Andy, and he is a research astronomer. He's trying to research, he's actually carrying on a research on these so-called cosmic fireworks, and he will be beginning his PhD very soon. Andy is also interested in data science, and very recently he's also spoken about the equality that needs to be there in science communication and the innovative methods that we can come up for doing the same thing. So without further ado, let me just quickly bring Andy in and we can begin. Hello, Andy. Thank you so much.
How's it going? Thank you so much for having me on the show.
That's absolutely my pleasure. I'm doing very good. So you've just begun your day, right? So we are 10 hours, 30 minutes apart.
Yeah, I just got my cup of coffee over here, and I'm ready to talk about science at 8 a.m. in the morning. So let's do it.
So let's begin. Yes. So Andy, before we start, would you like to add a few things to your introduction? Would you like to introduce yourself to the viewers?
I think you captured it all. My name is Andy. I'm an astronomy researcher. I'll be starting grad school in this coming fall, doing my astronomy PhD. Right now, I'm mostly working on supernova, so I'm really excited to talk to you about the cosmic fireworks, aka supernova. But yeah, we'll go into a lot of depth about these interesting explosions happening all over the universe.
Perfect. So I can understand the excitement around the word supernova. So let's begin with our episode. So how it's going to go ahead is that I'm going to ask Andy 21 questions. So I have pre-decided 21 questions, which are going to remain the same in every episode, right? So these are general questions about research, but can tell us a lot about what's going on. So let's begin with the first question that I have for Andy. And the question is, what is your research based on, and like what is the main hypothesis surrounding the research that you're doing?
Okay, great. So the sort of general target of my research is basically trying to understand how supernova can actually come to be. So in the universe, if you look at the night sky, if you know you're under a clear night sky and you look at the night sky, you would look at it and nothing would change. I mean, you would see the stars moving across the sky. But if you happen to have a really big telescope in your backyard and you were to look at really closely at the sky, you would see things changing. For example, you would see an asteroid passing or the planets in the solar system. But as you look farther and farther into the universe, you start to see some strange things. So for example, suppose you saw a galaxy every night, and let's say you visited this galaxy every night, and one night you noticed a little dot right next to that galaxy. You would say, well, what is that? And that turns to be that is a death of a star. So generally stars at the end of their lives, some of them actually end up going supernova at the end of their lives due to all sorts of astrophysical phenomena happening. So my research broadly tries to understand how stars go supernova, but one really important thing that we are trying to do these days is to basically discover as many of these as we can to do all sorts of interesting science. And, you know, of course, that's a little bit vague, but the sort of research that I've been working on is basically trying to understand for a particular kind of supernova, because there are all sorts of supernova, what is the distribution in their brightness? Because this turns out to be a really important problem in solving in astronomy. So these past few months, I've been working on what we call the luminosity function of core collapse supernova. So we'll decipher this as we go along, but basically all that you need to know for now is that the luminosity distribution means that you're just measuring how bright these supernovae are. That can help us understand a lot of more important mechanisms that govern these supernova.
That's actually interesting. And, as you said, that things change in the sky. So it always amazes me that people in the ancient past, those who've recorded, stone paintings and they've drawn supernova, how lucky they must have been. So talking on the same thing, taking that ahead, do you think we will get that opportunity to carve a supernova on our so-called slate?
Oh my God, that would be cool. I mean, like, so I don't know if you had heard like a while back, like people were excited about Betelgeuse. This is a star in Orion's constellation that they thought it was going to go supernova because, so the star is supposed to go supernova at some point. But of course we don't know, and the margin of error is really large. So people were really excited, like, oh my God, are we going to see a supernova in our lifetime? I mean, like astronomers were like going crazy, but turns out it's not, which is a bummer. The last time we saw a supernova relatively close to the Milky Way was in 1987, and it wasn't even in the Milky Way. It was in the Magellanic Cloud. So this were the satellite galaxies of the Milky Way.
Okay, so yeah, I do remember, the excitement that was around all the students I used to teach. So they were all like, so, okay, that star is going to burst very soon. So yes, it was a bummer that it did not. But I've actually, sometimes I've read somewhere that people have actually discovered supernovae, right? So if we cannot see them in a lifetime, how do they actually discover it?
So you don't need technically, I mean, here's the thing, right? Like people always think like to do astronomy, right, you need like the best equipment to like do something. But it turns out that the amateur astronomy community actually has done a lot of discoveries for, that end up going in like publications, right? Because that would be the sort of standard of like, how much impact is like what you're doing. So the astronomy community sort of in the academic setting relies a lot sometimes on the amateur astronomers. So amateur astronomers can have, like a 1 meter telescope in their backyard, something that you can get relatively cheap for. And, there's a whole online community of people who, for example, search for supernova, because supernova, the really good thing about supernova science is that they're bright. They're not like these faint sources. Well, it turns out that the research that I do specifically focus on the faint supernova, but technically the brighter ones are pretty easy to discover, even with like, a pair of binoculars.
Wow. So I guess that's a good motivational push to everyone who's just being afraid to step out and become a citizen scientist.
Absolutely.
So, yeah, you were saying something?
No. I was just gonna say absolutely. Like this is a great opportunity to just go out there and explore the sky.
Exactly. Take out your binoculars, take out your telescopes, and look up.
Yeah.
So that brings me to the second question for you, which is, why did you choose this topic for research? Why not something else?
Well, I think that going into sort of academia and research, I was always interested in sort of two main things. I love the stars. I love observational astronomy. So I love anything that has to do with like just looking, the visual sort of aesthetic of things. And that's why I sort of ended up doing observational astronomy. But I also had this huge fascination for data science, because I think that these two fields of astronomy right now are at the intersection. And what that means is that it's such a great opportunity to come into the field as an observational astronomer who also is very motivated to do data science, because we're getting all this data streams now from all these different telescopes and surveys, as I'll talk about a little bit later. So these were sort of my two focuses going into this my current job. And so I just found this, it was just, it just happened to be that this group that I've been working at was looking for a student. And my prior background was not even in supernova science. I studied stars in the Milky Way. So I was trying to understand what the shape of the Milky Way galaxy looked like using stars. So yeah, just happened to find it, and I've been in love with it since.
Yeah, so most people do not realize this, that when we say astronomy, we often think about scientists putting their eye at the eyepiece of the big telescopes and looking at things directly. And very
Yeah.
honestly, this was the picture even I had till a very young age.
Yeah.
So one thing that researchers who are going to come up in the future need to realize that it's a lot of data actually that we, or to say you, actually go through, right? So it's mostly
Yeah.
the raw data, it's the graphs, it's the intensity plots that are coming across, and that is why data
Yeah.
validation and programming is important.
Yeah. I mean, of course, you don't want to take the magic out of it in terms of like, right, like it is a lot of data and a lot of analysis and a lot of details and a lot of coding. And, of course, some people want that. And so you'll see a lot of astronomers sometimes are focusing more on the sort of data analytics part. There are people who focus more on the observational part. There are people who, focus more on the theory part. So yeah, it is a lot of data and a lot of analysis and a lot of time like on your computer. Sadly, not as much as time on a telescope with an eyepiece, but thankfully, because let me tell you, once you're like, for a week you're observing every night and your day and nights have been switched, it can be a little painful. So, I enjoy sometimes being able to take my time to wake up and go to sleep.
That's actually wonderful. But yeah, as you said, I hope I did not take the magic out of this wonderful field.
No,
It's a
no,
lot of data, but it's also a lot of fun.
not at all, not at all. That's the best part.
So, so that brings us to the follow-up question. That is question number 3. And the question is, how do you carry on this research? How do you try to prove the hypothesis or, disapprove it that you're going after?
Gotcha. Okay. So this is where we could talk a little bit about the details now.
Yes.
So generally right now I work for a time domain survey. It's called the ZTF survey. And basically what a time domain survey is you have this telescope. This telescope is located in Palomar Observatory in California. And this is a 48-inch telescope. And it basically tries to take pictures of the night sky every night. So every 2 to 3 nights, it can basically cover the entire sky. It scans the sky and takes pictures, okay? And then using reference images that we've been building over the past, what we do is we subtract one image from the other over every night, okay? And you have a stack of basically subtracted images of the sky. And basically what we do is throughout these images, we look for things that change. And of course, as I said before, like there's a lot of things that change, but among the things that change are also supernova. So the ZTF survey does this every night. It has an insanely massive field of view. So it's very quick in being able to scan the entire sky and find all sorts of things going, all sorts of cosmic explosions. So ZTF has been running since around 2018. And we have quite a big sample of supernova. So the way the process works is that we're a pretty big team, and we go through the data every day. Currently we go through eye. We of course have all sorts of filtering criteria that we go through the data, and we use machine learning, for example, to sort out, like, if you subtracted 2 images from each other, sometimes you would get artifacts. So we use machine learning, for example, to sort of throw away the ones that are probably most likely not real. So we go through these candidates of supernova, and we say, okay, this looks like a good supernova, right? We could basically track now the change in the brightness of the supernova. So once we've identified it, and the telescope visits the supernova again, the next day you could see sort of how bright or how dim it gets. So based off of all these criteria, then you rely on a series of other telescopes, and this could be around the world, where you basically take a spectrum. So you can now see the chemical composition. So once we get once we get a spectrum, we can then say now what kind of supernova it is. So supernova generally fall into, I would say, 4 classes. You have your 1A, 1C, 1B, and type 2. All you need to know basically is 1A are basically a binary system, and usually the 1 star is a white dwarf. And then the rest of them are what we call core collapse supernova. So the 1C, 1B, and type 2. And based off of some chemical footprints, we could tell, oh, this is a type 2 versus a 1B. So like a 1B, for example, has a lot of helium and not a lot of hydrogen, whereas, your type 2 has a lot of hydrogen. So, sometimes once we have the spectra, we can then say, this is our supernova. So now we have our sample of supernova, and now you could do science with it. Because of course, when you want to publish a paper, for example, you usually want to have like a sample of a supernova. Of course, there's papers on, just one individual object if it's quite interesting. But yeah, this is sort of how I'm currently carrying on my research.
Okay, so you said that there are 4 kinds of these supernovas. So which one or which class are you actually interested in?
So I study the type 2 supernova. And the reason why I study type 2 supernova is because type 2 supernova are the most common kind of supernova. Well, this varies, sometimes, but in the samples that we have, it's about half of our sample are type 2 supernova. So this could be somewhere in the order of like 300 discovered in just 1 year. Yeah, so they're quite a few. This is also, so you obviously might ask, like, okay, like, well, how do you, like, I mean, yeah, you search for type 2 supernova, but like one thing that you have to think about is like, well, how do you know where to look, or like how do you know like how to like restrict your sample? Because like, like when you're doing an experiment, right, you need to have an experiment design, a sort of controlled environment, so you understand fully what's happening within that environment. So in supernova science, there's usually 2 sort of ways to how to separate, sort of how to control the environment, if you want to say. Well, there's really one way of just basically just scanning the entire sky and whatever you find. But the problem with that is that you might be biased, right? Because what if, for example, I don't know, like your telescope is only looking at one particular part of the sky for whatever reasons, you might introduce a bias. So right now, so the sample that I'm working off of is what we call a volume limited supernova sample, meaning that we only search for supernova within a certain radius from the Milky Way galaxy. So this is 250 megaparsecs. 200 megaparsecs. Sorry. Yeah. So this is quite a bit. It's like I think it's like I want to say like 500 million light years.
Oh wow, that's a lot.
It's quite a bit of a bigger radius. So once we identify the supernova, so what we do is we have a catalog of galaxies. We know how far these galaxies are from the Milky Way, roughly, and then once we find a supernova that's next to that galaxy, it's pretty likely that this supernova would be associated with that galaxy, because you can also have something in the background.
You can map the distances.
Yeah. There might be a supernova back here, and like you're seeing it through the galaxy. So we know that, and then we just proceed to do the follow-up. So that usually is what we call like a volume limited supernova search.
So that's actually very interesting. So 200 megaparsecs, is it very big compared to our current, what we call the universe? Like, I know the universe is actually very big, but in the course of the daily science that is done, is it a very big scale, or is it
not at all? 200 megaparsecs is what we call local. It's pretty local. Yeah, we call, like, the experiment is called the census of the local universe. So it is, because like this is I mean, if you're familiar with redshift terms, this is redshift 0.05. And I mean, we discover supernova at like redshift 2, redshift 1, I think higher than that. But yeah, this is very local. And the reason why you do this is because the closer you look, the advantage to that is that you could discover supernova that are fainter, right? Because if it's fainter, that means that what we call the limiting magnitude you'd be able to discover things that are much fainter, closer. And then there's, of course, experiments that do this based off of a criterion based off of brightness. So if the supernova becomes brighter than a particular threshold, then we would save this and use this in our sample. So that's another experiment that we've been also running.
Wow. So this local experiment, really gives you the sense, okay, so the universe is that big. So we are very small compared to the universe.
Oh yeah.
Existential crisis kicking in anytime soon.
Yeah.
So moving on to question number 4. So is there anything interesting in particular about the research that you do? Something, that would make someone else interested in it or someone else jealous of you, something or the other about the research?
Oh, not say jealous. Well, no. Okay, so let's see. Interesting thing. Okay, maybe I could describe a little bit about some interesting stuff that have come out of this research that I've been doing. So one thing that we've discovered from this luminosity distribution. So, now we have the sample of supernova. Now we have what we call their light curves. So we basically have their full sort of evolution of what the brightness did. Okay. At the peak of the supernova, so a supernova has like this characteristic rise. It peaks in brightness and it gets the brightest, and then it fades and it does all sorts of things. So at the peak brightness, you basically just measure, how bright it is there. And you sort of apply all sorts of correction criteria because, as we said, we don't want to be biased. And so we have to remove all the biases that we have about our sample. So we did that for a sample of type 2 supernova running from this experiment. And what we found is that the distribution, so I'm going to introduce a little bit of stats here, but what we found is that the distribution is not just a simple Gaussian, what we call. So it's not only just like one little bump in the data, right? You would expect that they all fall within this range, right? It's a pretty narrow range. It seems like we're finding some structure in the distribution itself. And the structure is actually centered around two main points. So you have the brighter ones, but then you also have a fainter one. So these are called like subluminous type 2 supernova. And this was sort of seen before in the literature because, of course, when you're carrying out research, you always want to see if you're getting consistent results with others, or else something's fishy. And this has sort of seen before in other research projects, but this is the first time that we are seeing a very concrete evidence of it because. Wow. Again, the survey that we're carrying out, the experiment that we're carrying out, is very, very painfully. We follow a lot of rules in like how we save these candidates and like how far they away are from their galaxies. So we sort of have a pretty good idea of our biases against all sorts of things searching for the supernova. So this was sort of unexpected because. Of course, this has never been found. This has never been talked about in the literature of research. And some people might wonder, like, well, why should we care, like, how bright supernova are? And there are two main interesting things that come out of that. One is that, of course, you want to know how bright a kind of class of supernova are, because when you're designing future surveys or you're trying to find that kind of class of supernova, you want to have a pretty good idea of how bright they are. But one of the really important things is that you want to know the brightness, because the brightness, or what we call the luminosity, actually tells us a lot about how often these supernova go. And this is what we call the supernova rates. The supernova rates are important because basically supernova are responsible for enriching the universe with heavier elements other than hydrogen and helium. Right? So if we can basically think of it as like this: if we know how every day or every second how many supernova are going off in the universe, you can basically extrapolate, given that how much material they're spewing out into space, and basically then you can calculate how that incorporates into like how heavier elements in the universe are being produced, and like at that rate. So if those rates are matched, you were good, but it turns out that the rates are not matching. Well, there's a lot of tension actually in the research. So some researchers think that the rates between the supernova and the sort of what we call the star formation rate. So basically, that's a measure of like how much I would say a galaxy, how efficient it is in producing stars. There's all sorts of stuff. You basically compare those two, and those should be consistent. But there's some tension between the literature. I can go in a little more detail about that, but it's a lot of details to it. Yeah.
No, but that's actually interesting. The thing that has been seen in literature before, but no proof. It's more of you're believing what someone says. But over here, you have come up with the proof for something that's actually very weird, as you call it.
Mhm.
So, personally, I would say, as the public who's looking at this and who doesn't know that, why two different concentrations would be weird. I would say that I am actually jealous of you for the reason that you have been to so many observatories, right? So I am over here in India. I'm reading about these observatories, and then there's you posting a picture with one of those observatories, and then
Oh
over
my
here I'm
God.
going like, okay, yeah. So
Yeah, no,
that's the difference in my life.
it's always a pleasure to just go visit observatories. Well, yeah, sadly I haven't been visiting much since the beginning of the pandemic, but actually my last time I was in an observatory was literally 1 year ago, before the US went on lockdown. So I'm definitely looking forward to being able to travel again and visit various observatories.
Right. So, talking on that, as you said that you've not been to a observatory in a year, but you're still carrying on the research. So, people often think that astronomers have to be there with the telescope, but with the age of digitization, it has become so convenient for everyone.
Yeah. Yeah, yeah,
Okay.
yeah. We don't. So yeah, we don't need to be going to the observatory. As I said, well, I forgot to say that the way that the ZTF survey does sort of the scanning is through robots. We have the telescope is semi-robotic, so it basically can scan the sky. It's like you. I wouldn't say you click a button, but there's a sequence of stuff that you do.
Right.
There's particular scientists that are assigned to this, and it basically, they check to make sure the telescope's running well, and then it does it. It does it on its own,
So
and then the
someone,
data gets sent to us. Forgot to mention that
so,
part.
so somewhere someone's going crazy that robots are taking over the world, right? They're taking away.
Hey, robots are astronomers' best friends. I want a robot to just take observations for me so I can be sleeping
Yeah,
at night.
our friend Percy is out there doing research so that we can sleep peacefully.
Yeah, yeah, yeah. But when we're using the bigger telescopes, so I mentioned that when we're trying to get spectra, for example, of supernova, we do need to be. So what we do is we do virtual observing, and what that means is that we connect through our computers through virtual servers, and we are able to basically control a telescope, in some other part of the world, or if in this case it would be here in the U.S. And so that is a little bit more interactive. So for that, you have to stay up, quite late.
I guess that also answered a little bit of this, the next question that I was going to ask you, which is what kind of equipment do you use for your research? So I guess a little part of that has been answered, and I would like you to continue with that.
Yeah, yeah, yeah. So equipment, I would say, is my laptop. That's like my best piece of equipment. And yeah, we use a lot of telescopes. So the classifications that we try to get from these supernova are from all kinds of telescopes. It's not only one specific telescope that we use to do the follow-ups. So most of the times what I use particularly is at the Palomar Observatory. This is a 5-meter telescope. And we use that, like, we have a schedule, and there's usually like a night where I'll be on, and I'll have a list of targets that we go through, and it's just basically throughout the night, like basically trying to the art of observing is a really difficult one, and I always wonder if I should maybe one day live stream what the process is like, because it's it's awesome, because of course you're using a really powerful telescope. I mean, when you're there, when you see the 5-meter telescope,
Right.
oh my God, it's so big. It's like you're looking up. But it is a difficult thing, because throughout the night you have to make these really important decisions, and the last thing you want to do is be thinking really hard in the middle of the night. So there's a lot of preparation that goes into it before you go on sky, to make sure that that you could do the least amount of heavy thinking throughout the night, because you get tired. There's all sorts of stuff.
Yeah.
Yeah.
Right. So it's mostly the laptop on the forefront, but powered back by the big telescopes.
Yeah, 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 and of course, people. The best part about doing research, you actually, what? I take it back. The best
Collaboration.
part of equipment is the people. It's the interaction with the scientists. It's the ability to just collaborate with people, and I think that's honestly, anyone who's interested in doing astronomy full time. That's honestly the best part. Just working with people and collaborating.
Yeah, I think that is one of the major, bedrocks of good science, I would say,
Mhm.
because there's bad science also, but good science is collaboration.
Absolutely, absolutely. Yeah, that's one of the that's one of the best parts.
So coming to the next question number 6 for you, Andy, is that could you tell us a little about your previous past academic journey and how starting from obviously you did the normal schooling that everyone does, and how was your approach after that, academically speaking? What got you here?
Okay. Do you want me to go as back as like high school, or do you want me to like stay within the
No, no, no.
college?
Like yeah. So high school, I guess, is common for everyone, right?
Yeah.
So after that, what were the academic courses that you opted for, and
Mhm, mhm.
the decisions that you took academically that
Right,
brought you here?
right. Yeah, yeah, yeah. So, right. My path in college was a little kind of long. So I spent like 6 years in college because I grew up outside of the U.S. So when I came back to the U.S., I was born in the U.S. and then I left and then I came back. It was a lot of back and forth. Um, so one of the disadvantages to that was that I couldn't enroll straight into a regular
Mhm.
4-year college here in the United States. So we have here what we call community colleges, and that's basically they're meant to be 2-year programs. And this was
Mhm.
by far the best experience I had because, like you're in a space where everyone is just wants to get the education. So there I was just doing math and science. Really, I mean, of course, I knew I wanted to do astronomy. So I would take calculus and intro to astronomy and intro to physics. But then I met a professor at my community college, and we started doing research in what we call galactic archaeology. So I mentioned before that my
Yeah, yeah.
past was in understanding the Milky Way galaxy. So after that, then I transferred to get my bachelor's degree. So that took another 2 to 3 years. And at my undergraduate institution, I was majoring in astronomy. My sort of focus even back then was observational astronomy. So I would take classes like, observational astronomy. I would
Yeah.
take this class called astrostatistics that I really liked, where it's basically learning statistical methods to apply to astronomical data, which is a very useful skill to have. Some other cool classes that I took were modern stellar astrophysics. So understanding like the astrophysics of like how stars work is a really fascinating course. So then after that, I graduated, and I had the option to move on to go to graduate school or take on what we call a post-bac research position. So that's my current position, and I decided that I was going to take a post-bac. So I've been doing a post-bac now for 2 years. And yeah, I'm kind of sad that the journey is ending now, and I'm going back to school.
But I recently started my schooling again after a long break. So it does feel out of place. But
Yeah,
then again, I think going ahead for a PhD, it's just going to take you into a more interesting niche of that same thing that
absolutely,
you're doing.
absolutely, yeah, yeah, yeah. No, I'm really excited about it. I think that I, when you're excited about school when you're like reading before school starts. So
Right.
I think I'm on a good track.
So bachelor's over there is like 4 years.
It's 4 years, yeah. The bachelor's 4, and then a PhD in the U.S. usually lasts for about 5 years.
Okay, so over here, actually, if I talk about Bachelor's of Technology, that is around 4 years.
Mhm.
But for the pure sciences, which I did, it was 3 years.
Oh,
So,
wow.
but then again, I think the disadvantage over here would be I frankly have not heard about something like a post-bac, in over here in India, which is something I think if I was given the choice, I would have taken that for going in research.
Yeah, yeah. Postbacks are fairly new in terms of astro. You would hear postback most likely someone doing like pre-med, like a lot of
Mhm.
students who want to go medicine, like do like research in labs before they even start med school. Um, it's not as like organized as like it sounds like here in the US. Like I wish I was gonna say like, yeah, like you could just go like on Google and you could find like a bunch of postbacks. Like it is a lot of painful like emails and asking around and trying to see who has it. But the postbacks really are not. It's not like you're. It's not like it's like a formal sort of thing. It's more like you try to find a group that has the funding to support you, and research organizations that need the help. And so, some people call it a postback, some people can call it like a full-time job, all sorts of things. But yeah.
So that was actually, I think that was an interesting choice to start with research, because that gives you a hands-on experience on what's going on.
Yeah.
So coming on to the next question. So once you're done with the research, how do you think other researchers can, continue the research, and what would be the implications if the hypothesis is, proven?
Yeah. That's a good question. I think that one interesting implication that's going to come out of this paper that I've been working on is this fainter part of the distribution, right? So it was pretty well known that like these type 2 supernovae were somewhat bright, and this sort of secondary lower luminosity, the fainter type 2 supernova are actually quite fascinating. So I think that looking into the future, there's going to be a lot of focus, and particularly even for mine, because I mean, like, we're basically almost done with the paper. So a big focus of mine now is, and perhaps even in graduate school, is focusing more on these fainter type 2 supernova, because the question is now, like, why are they fainter? Is it, are they, because sometimes in astronomy or just in science, you can have a mixture of two populations, right? You can have rabbits and you can have, I don't know, like cats. But maybe when you look at their fur, and you were to just plot, let's say, fur as a function of size, maybe they would like look similar. But if you look at some other parameter space, you would see maybe that they separate. Not to say that supernova are bunnies and cats, but the question is are they inherently the same kind of explosion? Because that's a really interesting thing to think about. If these are actually two separate kinds of explosions, and one of them is just lower energy, so that's why it's fainter, or if there's something else going on. But one thing that I do suspect, it has to do with dust. Dust is the astronomer's worst enemy.
That's everywhere almost.
Yeah, that's almost everywhere. Yeah.
So I really, I'll be waiting for the paper to be published, and I'll definitely, read it, and I want to learn everything that you said. It's going to click back, and I'm actually, it has sparked my interest. So I just want to see how this goes ahead.
Absolutely, yeah. I'll be most likely sharing the sort of results soon on my Instagram. I've been even thinking of like a video on this, but yeah, it's been quite a bit while since I've been working on this project, so I'm really happy it's coming out nicely.
Finally, research actually, it's tough. So whenever it's going to come to an end, all the researchers are going, yeah, finally the paper is going to come to an end.
Yeah, it's like, oh my God, I'm like ready to move on. But it makes you appreciate. It really makes you appreciate how science is done, and science is as fun as it is. It's also, there's a lot of details that go into it. There's a lot of, it just makes you appreciate like. It just makes you appreciate like when someone makes a scientific discovery, you're like, it takes a lot of work. It takes a lot out of someone. So it really just puts things into perspective. Like, wow, like research is really exciting, but it does require a lot of hard work. But I think that anyone can do it. It's all about sort of just being methodic. Science is like just follow the instructions, document everything, tell us how you did it. And and then you just leave it up to the community to figure out if this is sort of something that will pick up, or if it's just an idea. It was just a hypothesis.
Yeah. So as you said, a lot of time it does happen that the community may at that point decide that, okay, this research is just an hypothesis, not something very important. But years later, people just find it out of the dirt to say and figure out, okay, so this is something that had already shown what we are trying to study right now.
Yeah.
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 So the best thing about, as we already said, was the community work that is done. So coming on to the next question, eight, that is, so we've already talked a lot about these things, but would you like to add to the interesting part of the main object, that is supernovas that you're studying?
Okay, so I wouldn't say there's one main object, but I would say there's n
Yeah.
objects. As I said, right, there's these very faint type 2 supernova, and we don't know why. And I am fascinated to figure out why this is happening. And as I said, we think that it's dust. And this problem of dust is actually quite an interesting problem, because I mean, it's impossible to sort of figure out in terms of like, okay, so you have a supernova happening in a galaxy, okay? This is going to be kind of hard to show like this, but a galaxy is a three-dimensional object, right? And a galaxy also can have all sorts of inclinations. So you can have a galaxy that will be like this. You can have like a face on. You can have edge on. You can have all sorts of orientation. Depending on the orientation and the location of the supernova might be experiencing what we call, well, it does, it's called extinction. Basically, what that is that the intrinsic brightness of the supernova is reduced because of dust. The light has to go through much more paths of, all sorts of particles, dust particles, for it to reach the Earth, and for us to observe. But one problem is that we don't know if when supernova are exploding, they might be actually creating their own dust. So they might be obscuring their own selves. And there's no way to sort of tell between the two. I mean, there is, but we need much more detailed follow-up. And you have to remember, right? Like if you're discovering 300, well, I should say there's more. There's maybe 500 supernova, let's say, within a year. Okay, type 2. Only these are for type 2 supernova.
Yeah.
The resources are really difficult, because think of it, like if you're observing once a night, once every month, using a telescope to get the spectra, and you're classifying these, it becomes a really hard resource challenge, because you want to discover as many type 2 supernova, but at the same time, how do you optimize the basically a more detailed follow-up of these supernova? The more data you have, so for example, if I were to use the Keck telescopes from Hawaii, right? These are one of the most powerful telescopes in the world. Yeah. If I get a spectrum from these telescopes, it's like, oh my God, pure gold. It's raining. It's like raining gold. Yeah, we praise when we get spectra from Keck, but there's also the question of we want to just get a classification and move on. So it's going to become a really interesting challenge, because we need more detailed information about these supernovas. So it's basically trying to figure out of all the data that we can collect right now, what can we extrapolate? What can we learn from these supernova? So all to say that in my project, we're basically trying to introduce some new methods of how we can basically calculate how much dust is being contributed from the galaxy. Because, right, as I said, the supernova might create its own dust, but a galaxy also has its own dust. So there's all sorts of components that we have to account for. So we think that we have a pretty solid method for calculating this. But it's still a really interesting puzzle to figure out, and I've spent a lot of times thinking about this issue, and it's just amazing to go in the literature and see and just feel the struggle of other researchers. People are so frustrated about it, and then you're like, damn it, I'm frustrated about it too now, because there's no one has an answer, and that's the magic of science, when it's you find something that no one has the answer to. And I'll never forget walking up to some research scientist and being like, hey, this is a hard problem, how do you do this? And they're like, well, this is science, you signed up for it. It's been a learning curve.
Wow, I cannot imagine not having answers, as a curious person, right? So that keeps eating you up from the inside.
Yeah, yeah,
Okay,
yeah.
so taking it up on that very note, that you spend hours and so many days thinking about it. So how do you balance your research life, the stress that you're getting from that, and how do you balance it with your personal life?
That's a hard one. I mean, these days because of the pandemic, it has been more difficult to balance this. Um, the reason is because we're all working from home, and
Right.
your office is your home, and sometimes it's pretty hard to step away from research. And of course, research is kind of difficult in the fact that you're always thinking about stuff, right? Like you're always thinking about a paper or something. Um, so I try to actively, you have to force yourself sometimes to take the step back. So I try to actively tell myself I have interest outside of astronomy or research or your work. So these past few months I've picked up cooking. So I try to just force myself to just okay, no more research. It's done. I'm gonna just do the hardest recipe that I can think of. That way I can just distract myself. But in times of non-pandemic, I love just hiking and going rock climbing and surfing. So, the outdoors is great. But I'm hoping that things will start going back to normal soon.
Yeah, so I guess the pandemic has given us, all of us, a particular hobby that we otherwise would may not have taken up. So talking about your cooking, which is the last dish that you cooked, which you're actually proud of? Okay, so I actually meant to say.
Oh, I made pizza the other day. I made my own handmade pizza. I
Okay, so
can't.
from scratch?
Yeah, from scratch. I
Oh,
can't say it
wow.
was good, but I'm trying.
Amazing. So I love pizza. So maybe one day we could just sit together and have a good slice of pizza.
Absolutely, you'll be my guest.
So, taking it on from there, the question number 10 that I have for you, Andy, is what are your tips to communicate a research paper in under 5 minutes?
Okay. Let's see. A research paper, I think there's sort of two levels of reading well, maybe three levels. No, maybe two. Yeah, two levels. Two levels of reading a research paper for the following reasons. When you're doing research, you obviously want to be caught up with the literature. You want to know what's going on, right? And as you sort of start to be familiar with one topic, you are able to sort of understand all the technical terms, right? What is a luminosity function? You just start reading a bunch of papers and you see how people use it and you sort of catch up with the language. So when you first start out doing research, it's quite often to just sort of skim through papers, basically just, what I personally like doing is reading the abstract and looking at the figures. If I see a figure that looks pretty cool or looks quite interesting, I'll read into a little more detail. And then another level of reading a research paper is just going through the details and reading the methods, trying to reproduce it sometimes if there's something interesting that you're particularly fascinated by. Some other tips that I have about reading papers is taking notes, which is really important. I'm a big visual sort of person, so I really love graphs, and I think that a paper should be able to communicate most of its science through its figures, because that's where all the power comes from the research paper. I could tell you, so we have, of course, arXiv, which is our sort of standard for reading research papers. There's a bunch of services online that have all the recent papers that have been published by a specific field. So yeah, I'm trying to think of any other tips for reading research papers. Yeah, I mean, I don't really tackle it I don't do anything different if it was some other textbook reading. The thing with research papers is you have to I think that the question you have to ask yourself when you're reading a paper is this useful for me? Because sometimes papers are really long, and you don't want to spend your entire day reading one paper that might not be even related to something that you're interested in.
Yeah.
So why put yourself through all that pain to read a paper that's not going to give you anything? not to say that, you don't want to read papers, but it's the skill that you have to acquire to basically try to figure out, like, is this something that I can learn? Is this something that, like, can I benefit from? Or is this just something that's not really related to my research topic?
Right.
And as the years go, you sort of get better at that skill. But I think that the main thing is like reading the abstract, and the abstract usually contains enough of information for you to decide if this is something you should continue reading or not.
Thank you so much for sharing those tips. Even I'm going to now follow those, because I think they are actually helpful. Because sometimes it actually happens that just to stay updated, we are like, okay, I'm going to read all the research that is coming up. But then again, as you said, research papers are usually very long. So you need to filter out which one's actually going to, help you out in the particular field that you're going into. And then the other research can be, followed up through the different news articles that come, and you really don't need to go into the depth.
Exactly.
Okay, so following up, and I guess a little part of this question has been answered earlier, but then how do you deal with the mental blocks during research and try to stay mentally healthy?
Yeah, those are hard. Those are definitely hard. When you hit a mental block, you're like, wow, like I feel like there's no escape. I think that the key here is taking breaks, taking as many breaks as you can. I mean, I don't know how brains work, but what's worked for me a lot in the past is sort of just stepping away from the problem. The more you try to figure it out, I feel like it runs away from you. But if you take a break and you just take just try to take a different perspective, I think that there's a lot of cool stuff that can come out of that. You just feel refreshed. If you give yourself like 1 week to, like, let's say, okay, I'm going to come back to this problem like in 1 week or in 1 month or whatever it is. You just think of it differently, right? Like sometimes part of something being difficult is because you just think about it too much. You're overcomplicating the situation. And then another thing that helps a lot with mental blocks is just talking to people. Again, as I said, science is a very social, astronomy is a very social sort of science. So talking to people often helps. Complaining to your colleagues, like, oh, like, why is my data like so bad, or whatever it is. So those are my coping mechanisms.
So first is like have a good support system, talk to someone, and take appropriate number of breaks.
Yeah. Breaks and talk to people, I think, have worked for me pretty consistently.
Wonderful. Wonderful. So I guess, yes, you always need someone to talk to. The more you're alone, the more you're going to overthink that particular problem.
Oh yeah. Oh my God. Yeah. And if there's no one to talk to, just like talk to yourself. Like, whew, you can catch me in my office. I'm just like, I'm having full blown conversations with myself. So
Role playing with yourself, basically, playing yourself.
yeah.
So now coming to question number 12 that I have for you is, how would you explain your research to a kid? Again, this is going to be interesting.
Good question. Okay. I'd be like, kid, do you see this equation? No. Okay, so I think that how I would approach sort of a kid to tell them about supernova science is, well, if you take a moment and you sort of look around you, and you have a table, you have a floor, you're wearing clothes, all this matter that we can see around us, right? There's a really fundamental question that we're trying to answer, right? Where does all of this matter come from? How okay, you have a table that's made out of wood. Okay, pretty easy.
Yeah.
Where does wood come from? From a tree. Okay, pretty easy. Where does a tree come from? Someone would say from the soil. Okay, fair. Where does the soil come from? Someone would say, okay, maybe soil is like, okay, I don't know, like some biological thing that's happened, right? Okay, where does that biological thing come from? You play that game, eventually you reach to a point where you can't say, well, how does that come? So you come down to the most fundamental question, like, where did all of this matter come from? And by matter, I don't necessarily mean like the atoms themselves, because of course that's a different question in science. But by what I mean is the elements like hydrogen and helium and the nitrogen and the oxygen that we breathe.
Right.
And understanding supernova. So when stars die and they go boom, there's like this massive firework. And, you know, as you said at the beginning, like we like to look at fireworks from the distance because you don't want to be there. But these violent explosions are so energetic that they spew out all that material into space.
Mhm.
And all that material that's been sort of cooking in the star and been creating all these heavier elements eventually lead into the galaxy. And these stuff end up becoming future solar systems and future planets and maybe future Earths or maybe us. So, you know, when Carl Sagan was talking about we are made out of star stuff, I think what he was trying to say is that we're made out of supernova explosions.
Supernovae.
Because the supernova is really the main engine of how heavier elements are being created into the universe. So understanding them is a really important thing because we can really come really close to answering that question. How did all of these heavier elements get to the universe?
And now, with this talk, you've left the kid just wondering, looking blankly at the wall and thinking, how did it come?
No, I have a funny story. I was like, so one time I was like doing like what we call Skype a scientist, and I had this classroom of like sixth graders asking me questions about astronomy, and these kids were like asking me like what happens like if you're going at the speed of light at a black hole, and I'm like, I cannot even answer these questions. These kids are too smart for me. I'm like, I can't do it. No, I think kids these days are way too smart for me.
The kids are smart for everyone. We have this method of dodging them by saying no one understands it, right?
Yeah.
But that's just to hide our own embarrassment that even we don't understand it, and we are
I know,
professionals.
yeah. But I think that like it's important that when you are in that situation, just spark wonder. Be like, yeah, like no one knows. Like I don't know. Maybe you could tell me. Like that. I think that's a much more powerful educational approach rather than being like, no, it's a bad question or something like that. So yeah, the
Yeah,
kids
so
are
always encourage questions, right?
absolutely.
And I guess, the speed of light and black holes, these are things that kids hear every day, getting other people, seeing other people getting confused by these. So they are
Yeah,
actually the center of all the questions that they ask.
absolutely. Mhm.
And I just wanted to ask something that while ago you said that the star bursts and it flies
Mhm.
away, and
Mhm.
that even I thought that, but a little while ago when I used to teach students, I heard that I read actually that before the star goes a supernova, it's actually collapsing, and
Mhm.
the instability of that collapse is actually what causes it to go out. So is
Yeah.
this the actual case that happens every time, or are there certain cases when instead of collapsing, it directly just bursts out like a normal cracker, like they say?
Yeah. So for core collapse supernova, yeah, it's in the word uh, core collapse. So it basically contracts. So what
Right.
happens at the end of the star's life is right. So now I'm going to try to explain a little bit stellar theory, but the long story short is a star is really dense, really hot, and it basically converts hydrogen into helium for a normal star
Hmm.
like our sun. Okay.
Right.
A bigger star. Now, not all. In the beginning, I said that not all stars go supernova, and one of the
Mhm.
main criteria that you need for a star to go core collapse supernova is that it needs to be greater than 8 solar masses. So it
Right.
needs to be pretty massive. So massive stars have the ability to basically achieve higher temperatures and higher pressures inside the interior. So these stars are capable of producing much more heavier elements like silicon and all sorts of elements. So throughout the star's life, these elements get stacked up, right? You
Right.
reach until you reach iron in the core. So once you start converting, once your elements start converting into iron, iron actually absorbs energy, and
Right.
so any element that's before iron basically emits energy. So that's how a star is able to shine and basically stay somewhat, somewhat big. And then
Mhm.
once it starts producing iron, the core, you basically are switching off the engine.
Right.
And once you switch off an engine for a star, that's not good news because you have the force of gravity now. And, gravity is a radial sort of field. So, everything's pushing
Mhm.
inwards. So a star is like starting to shrink and shrink. And the core will eventually start to get smaller and smaller. But then quantum physics happens. Um, and we have something called electron degeneracy pressure, all sorts of fancy stuff. And that core now cannot become smaller. So, you have all this matter coming in, and then basically it bounces up. And that bouncing procedure, is what makes the core collapse, the supernova go boom.
Wow, and that's as you said, it's one of the methods.
That's one of the methods, right? You can have a thermonuclear explosion, which is a white dwarf, orbiting some massive star, and some matter is falling from the massive star into the white dwarf. And then once you pass the Chandrasekhar limit, boom. But that's,
so I guess that's the type 1A supernova, that the thermonuclear one, that's the type 1A supernova.
That's the type 1, exactly.
Right.
Yeah. Whole different topic.
So, we usually say supernovas and we assume it's all the same thing, but then again, there's
there's a whole I always like to call it the zoology of the zoo of supernova.
Okay, so now once the kid knows what your research is about, we are going to come back to your research, to you particularly, and to ask you what was one of the major problems that you faced with your research, and how did you overcome it?
This stressed me out. No, I'm kidding. I think that, to be very fair, I think that this past year sucked, and it is really hard. I've talked about this a lot on my Instagram. Sometimes it's really hard to think about sort of astronomy when you see the world hurting so much. And for me personally, it was a pretty hard journey to sort of see all that stuff happening, and doing research that you all want to help the world, and sometimes there's like kind of weird guilt going on. But so I first want to just acknowledge that that was definitely something that not only myself but a lot of my colleagues also faced. And so in the middle of a pandemic, it's kind of hard to stay on top of things. But other than that, I think that, as I said before, this sort of problem with the dust and figuring out why these faint supernova are faint was a puzzle that's still kind of driving me crazy, to be honest. But it's driving me crazy to a point where I'm like, all right, now I just need to move on. It's basically like these supernova are faint. We don't know why. We have some theories of why this is happening. We think it's dust, but we're not entirely convinced. So this is making us rethink a lot about, why this is happening. But as the future will come, and there will be more detailed studies on this, we will be able to answer this question a lot more easily. Yeah.
So I guess the answer dust was the first easy to go to answer. But what if it's not dust? Then do you think there will be a major change in the theories of our understanding about supernova?
Yeah. If it's not dust, that's going to be a really interesting one. I think that it's going to be more interesting if it's not dust, because then what happens is that we would have to do an analysis to see what we call the progenitor masses were. So generally, you want to know what kind of star went supernova. We haven't talked a lot about the specific kinds of stars, and that's a whole another field of research, basically trying to understand what kind of stars these are, and if there's something weird about them, something interesting about them. So one thing that would be a really cool idea is to do a detailed study of subluminous type 2 supernovas, so all these faint ones, and see what their progenitor masses were. So what was the mass of the initial star that went supernova? And so I suspect that if they are very subluminous intrinsically, meaning that they are, and this is not an effect of dust, then I suspect that this would alter our understanding of the mass of a star going supernova. And that is a pretty serious thing, because then a lot of theorists would have to come into the play and tell us why, why it's this mass and not that mass. You always want to see what the limit is. And so right now what we're investigating is the lower limit, meaning how much little mass can you have before a star can go supernova? We're not sort of interested in the upper. The upper limit is also another interesting point, but I'm sort of more keen about that lower limit. Like, what's the lowest mass you can go before a star goes supernova, like a red giant goes supernova?
Right, but there's always this fuzzy line, right? It's not exactly a very sharply drawn line that this star will not go over
Yeah,
supernova.
no. Yeah,
There are
it's
always
like,
these stars that are breaking the rules.
yeah, there's a pretty big margin of error. So it's a really important thing. But again, as I said, it's an optimization problem because we don't always have perfect data. And like when you're doing a large statistical sample, the problem is that you have so many supernova to consider, and there's a lot of moving pieces. So you can't control all the elements. We don't have like finite telescope time where I can get like the most detailed data on like 400, 500 supernova. So you have to sort of work with what you have. You have to invent clever techniques to basically extrapolate interesting stuff out of it.
That's right. So it's going to be interesting to find out whether it's the simple answer, dust, or it's something new that's going to come out of the theory.
Yeah.
Before moving on, I would just like to say that I'm trying this software for the first time. So if the live feed gets over at 1 hour 6 minutes, I've already scheduled another live feed. So I'll just quickly send in the link in the chat.
Cool.
So okay, it did not get stopped. Good thing. So continuing our discussion, that's question number 14, which is assuming the research takes you into academia and teaching after your PhD. What are your opinions on that? And are you comfortable in the classroom? And what are your hacks to being a good educator?
Oh boy, that's a hard one. Yeah, I definitely love education. I think that, of course, I think I made a post about it the other day, like talking about education and just as an obligation of a scientist. Are there any hacks to education? I want to say yes and no. I think that I'm always sad to meet educators who have lost the passion and the fire to inspire students. I think that the things that have worked for me have been, energy, bringing that, people feed off of other people's energy. If you're, good morning, this is a supernova, who's going to care about it? But if you really believe in what you're saying, and if you really are excited about what you're saying, students feed off of that energy. But I think another really important thing is to listen. And I often find that a lot of educators don't listen. We only say because there's like this weird hierarchy in classrooms. And, of course, it's not to say in all schools in all countries in the world, but, my like education was outside of the US. And so, my classrooms in high school, for example, was this really weird dynamic between the teachers. A teacher is someone who's going to teach you like this is right and this is wrong. And that is a very wrong stance in how you should approach education, because a student quickly learns that the world is basically black and white. There's only a yes and a no. There's no in between. And when you're training scientists, a scientist has to basically be comfortable with in between. There is no yes and there is no no. There is no wrong and right answer. There's only just just your best educated guess. And we never really learn how to just go through that process in like our formal educational training. And that's because that's the part of that educators don't listen. They only assume that they're the ones that know the most. As we said before, like a kid might tell me something about a black hole that I never knew about. And so it's really important that we listen and we hear the need, hear what a student has to say. And the quicker the student realizes that science and education is a collaborative sort of discipline, the faster the student will realize that there's so many more possibilities to explore. So I don't know. It's a really tough thing to sort of perfect, and it takes a lot of years and experience to become a good educator, I think.
That's actually a very wonderful thing you said, right? I think a lot of people who are going to watch this video would agree that teachers play the main role in deciding whether the student later on is going to become a curious student or, just someone who's satisfied with what they've read. And I think sometimes it's also in the teachers that, maybe it's some ego, or maybe it's some embarrassment to not have an answer that we usually, instead of being embarrassed ourselves, we try to just cut down the question that's coming from the child.
Right,
So as
right.
you said, it's a collaborative effort. It's very important to listen to the kids.
Yeah, it's really important, and it's really important that we, listen to their needs. The needs are the most important part, because I think that back in the day, science used to be this very elitist process.
Yeah.
You look at, for example, the background of all these European scientists, right, in the golden era of physics, right. A lot of these people were rich. They had money to afford education, and so, you have these perfect circumstances for people to do science, but then you ask, like, what happened to all the other scientists? What happened to all the kids who had that possibility, but, maybe, finance was an issue. Maybe something was going on home. There's all these factors that go into it. Race plays a huge role into this too. Resources, it's a really complicated thing. And the problem is that, like, some educators just don't have the power to change that, and so they give in to sort of like, well, I just need to do my job. I need to teach students. They need to learn how to count. They need to learn how to read, and that's it. And we move on. But I am personally of the personal belief that we shouldn't move on. We should really focus. We should really, really, really be able to listen to our students and see what they need for us, so we can make them successful. Ideally.
I think you've touched a very important point over there, right? Something we, even the students after they've read it and long ahead in their life, we do not think about it, that how, if I would say this, that how male dominated and elitist the science was back during the golden era. So it was often like, even if there are, even the males in the field, right? If they do not have the money, they do not have the resource, they'll have to do the research that the richer person wants to do, even though it may not be the right way to go ahead. And then
Exactly.
obviously there were all the people of race, all the women who were, not being able to play the role they could have played.
Exactly.
So I am definitely, going to clip this part of the video out so that I can put it on Instagram, especially that I don't care if you're going to my YouTube and watching the whole video, but this is the clip that you need to see right now.
Yeah, and yeah, as you said it, like, for example, like women, right? Like, being on Instagram and seeing sort of this huge community of female scientists is so touching. I literally get goosebumps just thinking about it, because it's such a historical moment, like, to see, your colleagues that, that are not being judged by, their gender or their sex or, any of this. And it just makes you think, like, all these people throughout all the historical time of science, right? Like, how many opportunities have we missed? How many people who were as equal as impactful as Einstein or Newton would we have if society took a second to appreciate what good education means? But I have a bunch of theories why that didn't happen, but I think that would be for a different show.
Well, obviously, we are going to continue this talk very soon. So, after some really good words of wisdom, we come to the next question, that what is the most recent new thing or news that you've learned related to any topic? So it does not have to be supernovae, or it does not even have to be astronomy, if you will, but anything interesting that you learned.
Okay, yeah, I got you on one. So last night, I was watching this really cool documentary on a process called biomimicry, and it's this fascinating field of, I think it's like engineering and design, and basically what engineers are trying to do is design buildings and structures that are inspired by nature. So, for example, there's this fascinating building in Zimbabwe, and they basically, it's like this huge corporate office. And one problem that they had was they wanted to keep the space cool, during the summer especially. And they basically got inspired by termites. So it turns out that termites have like this nesting sort of structure that they could build really high up. And so researchers were inspired by that design to build that building that basically can self-cool itself. And I was just like, making me think, like, wow, like Engineers are cool. Maybe in my past life I should have done engineering or something.
So Sheldon Cooper doesn't agree with you, but I think this is actually very interesting. So I think yes, we should have certain hobbies, right? We should have subjects that we can return to because some people they want to read, but then if you're just reading what you're doing professionally, then
Mhm.
it's not going to draw a gap between your personal and your research life.
Right, right. And I think that like one really important thing to remember is that like, you know, my default would be like if you ask me like something interesting, I would like go default into astronomy where I'm most comfortable
Right.
talking about. But I choose not to because as someone that, you know, if you're interested in science, you always have to remind yourself that it's really easy to fall down the rabbit hole of like just becoming an expert in your own field, in your own sort of topics. But I personally like to just be able to go out of my comfort zone and like learn things about things that I don't know. And you sometimes are shocked to see the similarities between things. So the other day I was talking to my good friend, and he was telling me about like how you do research in biology, and we discovered that the biologists use a method that we use in astronomy, like for detecting exoplanets. And I was like, what? Like I was going crazy. But like that's like the best part because like you get to see the connections when you step outside of your field. And the more comfortable you are with stepping outside of your field, the more connections you can make with, you know, you're like, yeah, like if you don't understand it this way, maybe I can explain it in a different way. So yeah, I try to remind myself to just sort of, you know, learn things outside of astronomy.
And please just share that, the thing that your friend told you, because now I'm curious, what was it that I'm trying to imagine what is there in biology that can be detected the same way that exoplanets are.
Yeah, it's what is it called? I forgot the name now. Now you're putting me on the spot. It's called well, I forget the name, but basically what it does, it basically you give it a sample of cells and you shoot
Mhm.
like lasers at it. Well, like I think two like lasers to it, and basically the light that reflects off of the cells in two directions could tell you the size and basically the I think the thickness or the transparency of the cell. And then you can make a plot basically showing these two parameters. And you could see cell populations emerging. You know, like in astronomy, like we do the same thing for example, temperature and color of a star. Let's say, right? Like those two are correlated. So it's just like a very similar technique that we use in astronomy. Like we try to separate different populations using all sorts of parameters. So I was just fascinated to just see that there's a similarity.
Okay, so that's actually very interesting. I never thought that physics would have such a direct, similar method
No,
with biology.
no, it's actually pretty cool, I must say.
Okay, so coming on to question number 16, that is, if it was not for this subject, what would you choose to do in life?
I think, well, okay, maybe, okay. That's a hard one. I think I would most likely uh, probably try to do science still if I could. I think that I'm really fascinated by data and data science and
Hmm.
software. I think that there's a huge potential in that field right now. I mean, like we're at the brink of just like just this golden era of just data science and software. And there's actually this really interesting thing that's starting to come emerge right now, or that has been emerging, is the collaboration between software developers and scientists. Because scientists, of course, are trained to, you know, think and do math and do all sorts of things, but they're not formally trained how to develop software and properly. And that could become a pretty big issue because when you're starting to do programs in astronomy that require a lot of infrastructure and computing and software, things can get out of hand pretty quickly. So you need people who know enough of astronomy but also know a lot about software. So I think that would be something that I would most likely lean into more, is just the software, because it often mimics a
Right.
lot of the issues that we have in astronomy too. It's just like, you know, there's these challenges that you're trying to figure out, and like there's these rabbit holes of information that you go down. So yeah, I think software development would be my thing.
Right, and I think programming, as you said, it's a tool that astronomers these days need to know, because a lot of work that is done in astronomy is about modeling. And just a few days ago, when I was in my college, we were having this discussion
Mm-hmm.
on, that we should update our syllabus, that we are talking about the latest softwares like MATLAB and Python, right?
Yeah.
Because still in some colleges over here we have C++ being trained, which is not as common.
Yeah, C++.
So the models that you use, what do they use? They use Python or they use?
I'm mostly working in Python. Occasionally work in R as well for like statistics and stuff. Yeah, Python is the best language in terms because it's easy. It's easy to understand and it's scalable. I think that's the proper terminology, but it's just easy to get things going. And like there's also you want to find a language that there's a huge supporting community because
Right.
for example if like there's a new language called Julia, and this is sort of like a computational sort of thing, and the community is growing, but if I have an issue with Python, for example, I could literally just go on the internet and find my answer in like 2 seconds. Whereas if it's like a brand new language, it might be harder to find the information. But I think for Julia, the example that I just brought up, like there's a pretty solid community, and I think it's starting to grow even more. But the point is, you want to pick a language like Python that's easy, quick, 1, 2, 3, and you can just getting the research done.
Perfect. I
Yeah.
guess the friend you were talking about is watching the show right now, because
Oh.
he commented it's flow cytometry, the
Oh
technique you
yeah.
were
Oh
talking about in
wow.
biology.
I'm not on YouTube, so I can't.
He
Okay, there you go.
techniques,
Yeah.
but
Oh
yeah,
wow. Okay, you can hear me, right?
yes, I can.
Yeah, sorry. I just opened up YouTube because I couldn't see the comments. Oh, there you go. Cool.
Okay,
Yeah.
so
Commentary. Yeah, there it goes. Yeah.
flow cytometry.
Yeah.
So, as I'm going through the comments, I guess I'll just take a small deroute and I'll ask you something asked by one of our viewers. So, Samantha wants to know, out of all the celestial events that you've witnessed,
Mhm.
which one would you call your favorite?
Ooh, celestial events. This is a hard one. Well, okay. I want to say this is such a hard question. I think crap, this is a really difficult one. Okay, I'll give you two. One was a total solar eclipse in 2008, I think. This was back when I was a child. If you've never seen a solar eclipse, you have to see one. It's like the coolest thing that you'll ever see in your life. Like it's just like things just go dark. So that was one really cool thing. So if you ever have the chance to see a total solar eclipse, partials are fun, but I think total is like just magical. And then and really another cool thing about my job is that I get to discover supernova that no one has ever discovered. Like I'm like literally the first one to like see like, oh, that's a new supernova. So I can remember my first time in my current job when I was looking through the data and I found my first supernova, and you get like all the tingles going on because you're like, I just found something that no one else has seen. So that's always a very magical feeling that unfortunately, like obviously not many people can get because, of course some of our data is private. But it really, it just really just gets you going, it's just like, yeah, I'm like ready to do science.
So that's actually talking about total solar eclipses, right? That's even one of my bucket list items. So I've only seen the best I've seen is the annular solar eclipse, which I saw last year, and my first one was in 2018 or 19 actually.
Yeah.
So even I want to watch a total solar eclipse, and everyone who's viewing this right now, you can just post your comments or your questions on the comments, and we'll be coming back to them very soon again. And let's continue with the set of questions I have, because I'm the host, so I'm going to ask my questions first. So, so coming to question number 17 is there any particular piece of misinformation or pseudoscience that is common and pisses you off?
Oh my God. Yeah, I love this question. Well, I think all pseudoscience pisses me off. I could say that pretty confidently.
Preach.
I preach. Oh yeah, I will preach. I think that okay. I will say this. Misinformation that has to do with, especially during the pandemic, I think misinformation that has to do about public health is honestly the worst thing that I've seen. I used to think that like people who like who think that the earth is flat was like a pretty like, okay, like, why? But when you start to see information spreading about something about like health and life and public
Mhm.
health specifically,
Mhm.
um, that that just goes to show you. I think that this year we've all, especially for us who are like interested in like science communication,
Right.
we really gotten a taste of how powerful
Mhm.
misinformation could be and
Yeah.
how dangerous it could be and how careful we need to be with our own words and the information that we spread. With all seriousness, I mean, it's a very dangerous thing to do. I mean, people like doing all sorts of weird stuff and all sorts of weird stuff being on the internet. It really put into perspective for me this past year just how lethal science misinformation is. And of course, like when I meet someone who tells me, "Oh, you study astrology," now I won't go crazy. I'll try to use that opportunity to um, understand why. I think that the big problem in misinformation is that we often try to attack the people who believe in something that might be false. And remember, what we said is a big responsibility of being an educator is listening. And I think that often it's really easy to go down the rabbit hole of just being like, no, you're wrong. There's research, there's this, there's that. But instead of really trying to understand the train of thought, because I firmly believe that if you can construct the logic of like, okay, for example, like someone says the earth is flat, okay? um okay, the earth is flat, sure, that's your hypothesis, okay, let's do science. Like that's the best part, that like science is like you could do it. And so you could say, let's do experiments, let's try to figure this out, like let's look at the solar system. Do you see any other planets in the solar system looking flat? Probably not. There's all sorts of things that we can extrapolate. So helping people, encouraging people to not only seek their own answers, but guiding people to do science is, like public science especially, is like it's a very important process that I think could be a somewhat effective way of combating misinformation.
That's actually very well said advice that you give, because for the first time I'm actually, actively hearing this particular point of view, that instead of attacking them, instead of showing them the research, make them do it.
Yeah.
But then again, I think there has been certain, amount of research done in psychology that people tend to take it personally when their beliefs are attacked, right?
Oh,
Especially beliefs that do not rest on a rational proof. So at that point, asking them to explain a certain observation becomes invalid, because no matter how much proof, even if they see by themselves, they are going to find some logical, as per them, logical reason to counter what you've said.
yeah. Yeah, no, I mean, that's absolutely. And there's going to be, of course, the people who never give in. And so you ask, like, well, what do we do with those people, right? Do we let them, or, and that's sort of the trade-off that you get with like, like free speech and like, things not being censored. And that, of course, you're going to have a diverse array of opinions and thoughts and how people want to extrapolate information. And I think that I don't want to say it's fine, but I want to say that like it's a consequence of that. So you can't have the one without the other. You can't say then, like, no, I have to force you to believe this. No, I mean, no one should be forced into believing it. But I think that what we should do is then it's again a sort of optimization problem where, then try to reach to the people who are most likely to change and are able
Right.
to think about it more clearly, versus someone who's just, has their own ways about it.
I guess the best target for that would be the children, because they are going to be the future who are going to educate the next future.
The children are like sponges. They just absorb it all.
Wonderfully said. So now we are almost towards the end of 21 questions.
Mhm.
So the 18th question is, what are your views on science communication, and just share some of your experience.
Yeah. Well, science communication has been a fairly new journey for me. I think that, during my undergraduate degree, I tried doing a bunch of stuff in terms of within my university, helping students get
Mhm.
finding research opportunities and stuff like that. But at the beginning of the pandemic, I made this sort of Instagram account because I've been really fascinated to not necessarily share information about the universe, because I think that there are incredible science communicators out there already that are doing that. And
Mhm.
the good thing is that there's an overwhelming amount of scientists who are very excited about science communication, and it's a great thing to be involved with, especially now. What I think I've been sort of fascinated with is sharing the not necessarily the nitty gritty, but sort of the process. And I think that we often hear I don't know, astronomers discover a black hole or whatever it is, right? And we never hear like the sort of more human side of science, the more human side of research, the more, talking about the people, talking about the research that went into it, the all the stuff that go neglected. And I think that it's about time that science communication, we start to bring in the research component into our talks. It's not only like I'm going to show you and I'm going to teach you about physics. I'm going to tell you more about the trains of thought. I'm going to tell you more about the methods. I'm going to tell you more about the realistic things that like go into the day that, for some people it might not be interesting, of course, but for the students who are considering these careers, it's important that we as communicators, we show them what these footsteps look like, what it is. Sometimes it's difficult, sometimes it's easy. And so I think that using social media, like, could be such an incredible platform to deliver all the very practical information that we can to students. So yeah, this is sort of a direction that I've been thinking a lot about.
Yes, and also continuing on this. So this morning I actually had a meeting with a lady who was from India. Now she's shifted to Canada,
Mhm.
and we were actually talking about a prospective, science communication platform, and we realized that in India, if I were to say,
Mhm.
the field of science communication is very new, right? People have all these kinds of biases that if you're
Yeah.
into research you have to be this excellent person who goes into the laboratory, teaches. And if you're doing science communication, right,
Mhm.
that is something you're doing because you're not good in research, right? So you're doing
Right.
the lower kind of job. And even in this stage people are not if I were to speak of my country and my limited experience, I wouldn't say I've seen a lot of things, but in
Mhm.
my limited experience I've also seen that people are not ready to invest in science communication, right? So that does not become a job. We take it like, okay, so you're going to give a talk, that's not a very difficult thing to do, right? So why not do it for free or some meager amount of money? Assuming that someone of importance watches this video, and you have to tell them why science communication should be important,
Mhm.
right? Why it should be as important as research. So what would your answer be?
That's a good one. I think that what we've learned about science communication is the following. Um, Myself, including a lot of my colleagues, are the
Mhm.
products of science communication. Um, back in the 80s, sort of older generation scientists would say they saw the Apollo missions, they got inspired, which is incredible. Of course, there's all sorts of channels of inspiration. Not to say that social media are the only way to sort of go about outreach in science. Um, but at least for my generation, I could safely say that a lot of my interactions with people have been, a lot of us are a product of science communication, meaning that, like, we were the generation who like was going on YouTube and like, looking at Veritasium and all these sort of science communicators on YouTube, right? That like,
Right. Yeah.
we grew up in that, and like, or like seeing Carl Sagan's Cosmos series, right? We were the product of the people who were passing down that knowledge and passing down that sort of
Mhm.
awesome feeling of the like, whoa, like the world is so fascinating. So I think that it's a very powerful thing to invest in science communicators because they inspire the next generation of scientists. They're the ones who are leading the next generation of discoveries. And someone will say, "Well, why do we need discoveries? Like who cares?" Well, you care because your society relies so heavily on science and technology. So you would absolutely want scientists and technologists in your society, and to be able to train them properly. So yes, do support your science communicators because this is a very important part of being able to inspire the next generation of scientists, help them go through the path.
Very wonderfully said. I hope that's able to convince the people that yes, science communication is important. And okay, if someone's doing science communication, that is as good as I said. It doesn't necessarily mean they are a bad scientist.
Right. Of course.
Okay, so talking about science communicators and how we got inspired from them, name one scientific figure of inspiration for yourself and why.
That's a hard one.
And it's a hard one because you have to say just one.
Yeah. Yes, I will say just. I mean, okay. I'll say this. Obviously, it would be Carl Sagan. I think that I grew up with Carl Sagan, sort of seeing the Cosmos series. But for all sorts of reasons, Carl Sagan just has this amazing ability. I think that now, more recently, that I've been more actively involved with science communication, I start to realize how difficult it is to do it. It's not as straightforward as just like, hey guys, welcome to my science communication channel. Like it's a lot more, it takes a lot more thought because of course you want to be effective in what you say. And you quickly realize communicators, who are quite famous, it's a really difficult craft to master, and speech and being able to excite the public is quite difficult. And it definitely requires a lot of practice. But
Yes.
the reason why I hesitated a little bit was because I think that it's quite a touchy subject. I mean, we should have role models in science, but it becomes quickly out of hand because I think that I think one thing that you'll recognize, as someone moves on to academia and doing research, that we often get attached to figures in public, right? It's nothing. There's nothing wrong with having a role model, right? Whether that's science, sports, or whatever it is. The problem is though that we get attached to people, and sometimes people will do bad things, and people will do things that are so against our own values, and that's a very troubling thought. I mean, I could tell you a whole bunch of examples. Growing up, I used to read Richard Feynman, right? A great physicist, great communicator, right? But I could tell you very confidently that my community of my colleagues, including myself, there's been a lot of stories and a lot of proof that that Feynman did not treat women with equity and equality, right, and fairly. And this is a problem because how can someone be such an inspiring figure for you, but at the same time you learn all these things about this person or about this figure that go against your own beliefs? Do we say yeah, we separate it? And I think that there are several layers of that, of privilege, of where you could say yeah, I could choose not to think that Feynman was harassing women, for example, right? And because I'm a man, right? And I'm a male, and I, for the most part, men don't. It's not the same for women, right? For women that who might have had that experience in her life, that's something that's a no. So, long story short, I think that we have to be careful who we idolize, but at the same time, I think that it's okay not to idolize people. It's okay to just respect people in the community and be yeah, that's a good scientist, that's a good skeptic, that's that. But overly idolizing people is sometimes a gray area, at least for me, unpopular opinion.
Right. Okay, yeah, so we can also go about it in this way, that idealize the craft, not the person. because
I
in
don't,
the end of the day, he or she is a human, right? And they are going to have evil parts to them.
exactly.
So get inspired by the way they do what they do good, but then again, draw the line to not get over inspired. Because I
Right.
remember when I was in college, I used to study a particular part of my bachelor's by watching the YouTube series of a very famous scientist and teacher from
Mhm.
MIT, right? And I'm not going to name that person, but later on, I actually read news that there were, certain harassment cases against him, and he was, I think he was fired after that. I'm not sure.
Mhm.
But then again, then that's the point. Till then, I was idolizing that person, right? I wanted to be like him. His method of teaching was something that blew me away completely.
Right. Yeah, the only reason why I brought that up, and of course, it's easy to just move on and just say, yeah, like this person inspires me. It's really
Mhm.
important that, especially the younger audience, that they start to actively think about this. Who
Yeah.
are the people who we support? And as you said, you could support someone's craft without attaching it to the personality, but again, it becomes tricky sometimes, I think.
Yeah.
But it's just important that we just acknowledge that that's a real thing. So
Yes.
it's perfectly fine to have role models. This is not to say that we should throw away all of our inspiring figures, but I think that we just, like science, we should practice critical thinking, and we should practice safe and critical thinking. So this is just to say, think more, think more, be more skeptical.
Perfect. So, with that on science communication and idolizing people, we come to the 20th question for today, which is, what is one advice you would want to share with prospective graduates?
Ooh, one advice I would say is keep at it. Just keep going. I mean, it's science is a very long journey, and it often is very frustrating. It often is very rewarding, and if you are just stick with it and you just my advisor always used to tell me the following. She said, do science and do research only when you're having fun. When you stop having fun, she said, just drop it. It's not worth it, because it's such a consuming sort of job. So I think that just have fun. Just I think I want to spread that that message too. Like just have fun. Science. I mean, of course, you want to be responsible. This is not to say that we should just only prioritize having fun. But at the early stages of doing science, I think that it's very important that we remember to enjoy it, right? Like if you're like crying every day of like doing your physics problem sets, then maybe something's going on. Maybe physics is not for you. But if you feel like excited when you talk about it, I think you're on the right track. So just have fun with it, be responsible with it, and do it when you're enjoying it. Like don't waste your life on doing things that you don't want to do.
Right. So, just summing it up in just one word that you said, that be excited about it. That is very important.
Yeah,
Because
just get pumped.
yeah, because when you're not excited and you get into that field, you're going to become a professional. You're going to start a chain reaction of uninterested people, right? Who are
Uh,
going to come to science. So you're not
yeah,
interested. You're like, okay, yeah, you're just an old man sitting in your sofa and just killing the curiosity out of everyone who comes under
yeah.
you.
Well, I feel like that sometimes that's the product of like educators who have lost that
Yeah.
passion. It's like,
Yeah.
I mean, maybe some people were like passionate when they were younger, but like it's important that you keep that, because that when you're young and you're a student, right? Like you want someone who has the energy, who really makes you feel like there's like life into this. Why would I go into a research field that's like everyone's like, "Ugh, like this is and, you want someone who's woken up like, I'm ready to go.
But we have a nice attitude and energy at work. I guess that's the best thing. So with that, I come to my last question, and then
Mhm.
we'll just come to what our viewers have to ask. So the last question that I'm going to ask you is, I think, a simple one or not. If
Mhm.
you could suggest one book or author of any genre to someone, what would
Mhm.
it be?
Yeah, I thought about this. I think that it would probably be the Backyard's Astronomer's Guide. I think his name is Terence Dickinson. So this is quite a different suggestion for a book. The reason why I'm saying this book is because it was so I grew up with this reading this book, and it's a pretty hefty book. I think it's like 300 pages, but it literally walks you through the very foundations of like how you start astronomy, like with your own eyes, with a telescope, with binoculars. It explains how telescopes work. It explains how cameras work. It explains all sorts of things. But what I love the most about this book is that it teaches you how to do astronomy right now. Like you open the book, the first thing
Okay.
it'll start telling you about is like you can go outside and see this phenomena. And for me, like at the very foundation of astronomy, that's the thing that humanity did, was they just did astronomy. Astronomy wasn't only a concept. It was just it's a purely observational science in that.
Right.
Well, of course now it's more complicated than that, but at the essence of it, it's all about the experience, like looking at things.
Yeah.
And often when we said, at the beginning, like looking through a telescope, yeah, I wish that was more part of the job. So I encourage as many people as possible, if you can get a copy of that book. It's just excellent.
Would you repeat the name of the book? Even
Yeah,
I was going to type it down.
yeah, it's the Backyard Astronomer Guide by Terence Dickinson.
Backyard Astronomer's Guide. So definitely going to go through that book very
Yeah,
soon.
just
So
excellent.
So with that, after 1 hour, 45 minutes long discussion, where I've been, learning a lot. It has, I think, the best reason or the best advantage that I'm going to have with this series is it's a very nice learning experience. I think when because personally speaking, I've never had I wouldn't say privilege, but I've never had the chance to do research, right? To publish a paper. And that is something I'm going to do next year. So I just want to learn the process, learn what goes on in your mind, because even now when I sit, I'm usually thinking that how do I decide what to research on, and how is research carried on. So it was a very wonderful experience, but before letting you go, I hope you're not getting too late.
No,
Right, you're
no, no.
not too late. Yeah, perfect.
Yeah, no,
uh,
you're good.
so you've had your breakfast. It's early up in the
Oh
morning.
yeah. I'm an early riser.
Okay, then I'm not going to be guilty about it then.
No, not at all.
So, okay. So, coming to the comments by our viewers. So, if you're someone who's viewing this right now and you want to ask Andy any question related to what he does, you can type it down on the comments. And I have this question.
Mhm.
So, Neela Kates, he's actually one of my seniors in college,
Mhm.
and he wants to ask you that which one is important, more important actually,
Mhm.
observation or hypothesis in research?
Ooh, I like that one. That's a good one. Uh, I would say, uh, well, there's joys in both sort of this sort of pursuits. I think that observation for me is more exciting because I think that inherently humans are explorers, and I think that we love discovering things that we didn't know.
Yeah.
So a lot of times it's easy to go into science with the assumptions that you have, like, yeah, like I assumed that I would find this, and there's always a big rewarding part when you are right or wrong. And of course, a big deal of being a scientist is being able to be not biased about things. So to believe the things that nature says. But I think observation has this sense of discovery and wonder because, like, as I said before, like, you see a supernova, you see something that no one else has seen before, and that usually comes from observation.
Right.
Good question.
Okay, so there's the answer, but yeah, so okay, this is a really interesting question. So it's going to speak on what you were already saying about
Mhm.
idealizing someone,
Mhm.
and so the question is, knowing the science community from inside,
Mhm.
one could say that the environment is toxic, right?
Mhm.
So do you think that to become a good scientist, you have to forsake your humanity?
Yeah, that's a good one. That's a really hard one. Um, Listen, academia, like any space, could be very toxic. this is not to say that only academia is a place where these issues are coming about. I think that the community itself has been pushing more. I think that at least the younger generation has been trying to push more for more equitable environment. I mean, the thing is, like, academia is changing for the better, but what I'm more concerned about is the pace of things. One step in the right direction is, of course, really good, but we have to be able to identify where the problems are. We have to be able to identify what are the weak what are the weak parts in academia that we can further build on. And here's my thing, right? At the beginning I said, like, if only we can give all students in the world an equitable and equal access to education, right? What would the world look like? And it's a similar train of thought of, like, what would happen if we did that in the academic setting, right? Like, right now, like, you work for, let's say, some university, and this university could do this well, let's say in the field of science or whatever field of study. But the question is, if I were to improve some things, and if you were really to hone down on some things, that some weak parts to this, how much better, how much more yield you would be able to get, right? Like, like big corporations, right? And we don't need to say names, but like big corporations actively work on this. When you work in a job outside of, let's say, academia, and you see sort of the industry scale of things, the industry does not have a huge margin for error because they lose a lot of money, right? Like, for them, it's like, we can't lose money. We need to be able to make sure that everything works perfectly fine. And the thing with academia sometimes is that, like, things are not of great priority, meaning that, like, no one's losing money. Well, yeah, sometimes they are, but like, so a lot of these issues are not being necessarily addressed because some people are not prioritizing it. And this is not to say that industry is, like, better, like that they are doing a better job at, like, keeping their environment safe for people to work and stuff like that. But I think that as you start to shift and make the people more important than the science, that's when I think that's the magic spot, because we're living beings, right? Like, we have feelings, we have emotions. It's a dynamic situation, and as scientists, we know that we understand how complicated the natural world is. So, why we're ignorant sometimes. Some people, I think, are ignorant of their own chaos within their own social circles. So, all to say that I think that we're going there. Things are getting a little better, but I'm still a little concerned of the pace of how things are going.
Right. And I think we could also interpret it as saying that as an individual, do you need to change your ethics in a way to be a good scientist? And what I mean by that is, I don't mean that put down someone else's research. I don't mean if you're, don't give others opportunity to test their idea. But what over here I mean is lose that sense of humanly right or wrong. For example, if Einstein knew that his research would result in atom bombs, right? So should he have stopped doing his research, right? So should we be that level of logical, or should we have emotion, some level of emotional?
I'm gonna say my young self would say no, because when you're young, sometimes you might not think of the consequences of it. That's to say, of course, that if you're working in a lab where, like, you're working on an atomic bomb, like, yeah, it's a serious question. I mean, like, it depends on what your values are. I don't think that you have to change your ethics to do science, but I think it is time that we think more clearly. I mean, it is important that we do think about the consequences of the things that we do. And back in the day, maybe people would live their lives and, like, not really care, because it is, like, people just say, like, yeah, like, that's the way things are, and, like, I can't do anything about it. But we could take that same approach to many issues. We could take that approach to climate change. I can't change the world, so then why should I do it? It is taking a firm stance. And of course, it's a pretty complicated subject, but I think that like if you can, I say wherever you can put your ethics in front of your science. I think that's a pretty safe bet to say. Of course, not all is all science ethical. Again, I think that's just a whole different subject. But yeah, I think that we should be doing ethical science as well. I think it's a really important thing for the sustainability of humanity. It's not even about like the discovery or it's not sustainable to do science that's not ethical, because we fall into these perpetual traps of doing wrong things to people that don't deserve to pay the prices of that. The people's whose lives have been affected by nuclear bombs and bombings, right? Like like why did they have to pay that price? And I think that's important as scientists. We actively think about that.
Right. We should also not forget that science, in the end of the day, is being done by humans, right? Who are both good and bad. So in my personal opinion, I think every science should be done, but then it is on the values of the policymakers and the people to use it in the right way, right? Because I wouldn't want Einstein to not give his formulas or give his theories, because they have also done a lot of good things, right? Today we have GPS. Today we are able to do such amount of amazing things. Gravitational waves have just become a completely separate field of research. So I think science should be done without barriers, but whatever the result is should be put into good use. That is where the ethics part should come.
Yeah. And I think that's like, yeah, absolutely. Like, of course, like E equals MC squared, right? Like, yeah, like, of course. Like, I mean, it has so many implications for astrophysics, right? Like, I think that's the great problem, though. Like, how do you know? I mean, like, science comes in this beautiful packet, but it comes with no instructions on how to use it.
Right.
It's like, yeah, like E equals MC squared, but like you get to choose what the E and the MC will be, so it's yeah. I feel like sometimes it's kind of a hard thing to sort of figure out, but yeah, I'm definitely excited for all sorts of research areas, but it is important that policymakers and those who govern people they should be the ones who should be very carefully thinking about how technologies affect our lives. Definitely.
Yeah. So I guess that was one of the best questions that we had.
That's a very loaded question.
More of a philosophical question to think on. So I guess the last question I'm going to ask you today is that what makes astro so close to your heart, and how do you encourage youngsters to go research on astro rather than other physics fields?
Well, I think that like astro for me was like very close because like I advocate this for a lot on my channel for clear skies. I think that having a clear sky is a very important thing for future astronomers. And it's important that we maintain our skies and we keep our skies clear. That way we can inspire, like I grew up, like seeing every night the Orion's constellation, in the winter. And, I would always look at it and be like, wow, like it's so amazing to know that like there are stars there and there's all this stuff that we can't reach, but at the same time we know so much about. It's like this great paradox. It's like you'll never be able to visit this star that might be like thousands of light years away, but at the same time, you can learn so much about it just from the light. It just always blows my mind to know that like that actually is how far modern astronomy has come. And for people who are interested in doing research on astronomy versus other fields, like for physics, for example, I mean, I wouldn't say like I would say like, you shouldn't do physics. I mean, you should do whatever interests you. But I think for astronomy right now, this is the best time to be involved with it. There is undoubtedly, I mean, I could tell you my opinions on like other fields, but I don't think that's productive. But I think that astronomy right now is entering a golden era. I mean, we have the James Webb Space Telescope coming online. We have all these brand new telescopes that are being built all around the world. And most importantly, these telescopes are not being excluded from the public. And I think that's something that is happening more frequent and frequent. So it's just an amazing time to just be involved with the field, because there's just so many exciting missions and telescopes and stuff that are coming online that will just, we're going to be the generation that's going to be writing like new textbooks on astronomy, because we're learning so many new things.
That's right. That's right. And as you said, the fact that all the information that we know, every single thing about astronomy is just carried by those twinkling lights that you see from Earth. Right. And usually when I have to, talk to kids and talk to students and, get them interested, that is the point I go to. That, you're just seeing a white light, but this light is carrying all the information. And I just like to extend it to the idea that this light that you're seeing, which has so much of information per se, is just a very tiny part of the actual amount of information that is coming through.
Oh, yeah.
Right.
Yeah.
So that is why we need all these X-ray telescopes and infrared telescopes and things like that.
Yeah.
So you said very well that astronomy is going to is entering a golden age, and for me, personally, I'm also very excited for the James Webb to just launch. It has been delayed so many times.
No,
Every time it's been delayed.
It's become like the running joke, like like the world is gonna like solve like global warming before James Webb goes up into space.
So there's going to be a headline: when's the next date that James Webb is going to be delayed again?
No, I'm optimistic. I'm optimistic that it's going to be soon. I think,
Yeah.
I mean, it's definitely going to be within our our lifetime. So I'm hyped about it. I'm hoping.
Wonderful.
I'm
So I
cautious.
guess with that we've come to the end of the questions, and so wow, that was a very amazing session. So before I conclude it, I would is there something you want to say to?
Yeah, absolutely. I think that, well, I just first want to just thank you again. I'm a huge fan of your account, and all the amazing graphics that you produce is so great. I just wanted to take a second to acknowledge how amazing your work is. Like, I just saw your work and I was just like instantly hooked. So I just want to congratulate you, and like I'm really happy to hear that you're starting your new academic journey, and I wish you like the best. Like, obviously we'll keep in touch, but just keep up the amazing work. You're really doing a lot for this community.
Thank you so much. Thank you so much. So I actually remember, that one of the first texts that you sent me on Instagram was, "We should collaborate in the future."
Yeah,
And
absolutely.
at that point, I had just started the page, and I was wondering, okay, so now am I going to collaborate with people? And he's doing proper research, and what am I going to do? Am I going to draw something about his research? But then I'm very happy it came up to this, that okay, at least I got the chance to start this particular step of collaboration.
It's a great idea.
And I'm very sure that this dialogue that we started is going to continue for a very long time.
Absolutely.
So thank you so much, Andy, for joining us today and being the guest for my first episode of this series, catching up, keeping up with the universe. And it was the experimental part that does any technical issue come up, something goes wrong, and the backstage scenario that happened with the timing, right?
Yeah,
so we were possibly going to wake up on the wrong.
Absolutely. No, I'm glad it wasn't 2 a.m. for my time.
So with that, I would also like to thank every single of our viewers who've been joined with us since the beginning. And thank you so much for joining us. I'll be releasing the next episode very soon. And I hope you'll be there too. So thank you so much, everyone. Bye-bye.
Bye. Thanks for having me again on the show.